Hi friends, let us discuss today about monotonic functions and their relation with continuity. So if we see the definition of monotonic functions, it is having two parts. First is monotonically increasing function and second is monotonically decreasing function. That we discuss all in some interval, bounded interval AB or maybe unbounded also. And the function should be defined on its codomain should be R. So for that case, if we have monotonically increasing function, it means that whenever we are going to take 2 points between the interval, the x is a smaller one and y is a bigger one, then fx will be less than equal to fy. That's a definition which we learn in our 12th class also. So that's not a big new thing. So it's all just a recall of the concept. And same way, a more monotonically decreasing function is defined on that interval if and only if for the 2 points x and y between the interval, if we have fx greater than equal to fy. So that means it is going to be increasing function is going to be something like this and decreasing function is going to be something like this. So in that case, we have to discuss about its relation with continuity. So that's the result what we will learn as a theorem number 4.29 of the Principles of Mathematical Analysis book of Walter Rudin. So that says that if we have a monotonically increasing function, so particularly for increasing, it is writing the result, and similar result can be written for a monotonically decreasing function also. So for a monotonically increasing function defined on this interval, what happens? The right hand limit of this function at any point x in the interval and left hand limit of this function at any point x both exist at every point, means for every point on the domain they exist. And the second thing what it says is that the supremum from left hand side, if we try to find out for any particular x is fixed, so we are trying to find out if we see this in diagram. So if this x is a fixed point, so corresponding to that, if ft is slided over as t slides over in the neighborhood of x, then ft will slide like this. So what we are saying that if we have the for the dummy variable t and x being kept fixed for the time being, so between a to x, so if we have interval a here and x here, so in that case, if t varies in this interval, left hand side of it, and we find out the supremum, so what we get is the left hand limit. So fx negative will be here, and we will have a supremum of this because it's a non-negative, it's a monotonically increasing function. Same way, what the other part it says that f of x positive, that means the right hand limit of x, if we find out, it is equal to what? It is same as the infimum of those points ft where t is varying between x and b. So that means if this is x and suppose this is b, so in that case if t varies over this, then ft varies like this. So the infimum of that will be its fx positive, that means right hand limit. So that's how this part, these two parts are this one, this is equal to this, and this is equal to this is the this part, second part of this one. And over that means it is involving one more inequality, two more inequalities. The inequality says that for any x belonging to the interval, the fx, it will be between um, f of x negative, that means left hand limit, and f of x positive, that is right hand limit. That means right hand limit will be greater than equal to the left hand limit, and fx actual value will be in between those one. So that's what it is saying, it should be less than equal to here. So for a monotonically increasing function, if it is strictly increasing function, then it will be less than, strictly less than, exactly like this. So we have this one, and second part of this theorem says that if we have any 2 point x and y in between, then fx positive, that means right hand limit for the smaller point for the function will be less than equal to the left hand limit of the smaller point. So if I tell you like this, so let us say that this is x here, and therefore we have x positive, which is maybe bigger than or equal to fx, and here it will be y. So if it is y, then fy will be a point here. Its left hand limit means if we are approaching from this side, its left hand limit, which is definitely infimum of the all t such that all t such that t is between x y and sorry it is supremum of ft where a is between t and y, that will be y. So if it is y here, so that's how we are going to have fy negative and fx positive. So it is saying, as we are able to see from the diagram, fy negative, the left hand limit of this one, and fx positive, where x is this point, so fx positive, which is right hand limit of this point, they will be following this relation. So if the point is on left hand side, even the limit superior means right hand side, the right hand limit, the limit superior, as we find out from this one for x, this is smaller in comparison to the at the limit inferior at point y. The reason is same, because it is monotonically increasing. From the diagram, it is very much evident. We can learn like this. So let us quickly see the proof of this theorem. It says what? That if we have monotonically increasing function on a bounded interval, we are considering like that. So let us consider an x point. So what we are going to do for this x fixed one, so we are going to find out this inequality. So what we find out is the left hand side. So we find out the supremum of, because it's a bounded set again. Why we can find, first of all, the supremum what we want to find out on this interval of ft, on the interval atx. This set of ft such that x this t belongs to the interval a to x, it is a bounded set. Then only we can define something supremum, and then comparing with some real numbers like this, it is bounded set. Why? Because if we have fa and fx here, so it is bounded between the range of the set is bounded between those one, because it is a monotonically increasing function. So that's how we can define something called supremum of it. Let us say it as a, and now what we have to show, we will show that the supremum is less than equal to fx, and then we will show that this supremum what we have found out, let us say it as a, this is same as f of means the right hand limit of the function. So that means if we see here, so first we are proving that this supremum is less than equal to fx, and then we are proving that this supremum is equal to that right hand limit. So these are the two parts in the first part of the proof what we are going to do. So that's how we are able to prove. The reason is very very simple, that supremum of this set, because it's an increasing function ft, t is between a and x, so t will be less than x. So what is going to happen by monotonic function definition, monotonically increasing function, because t will be less than equal to x, so ft is less than equal to fx. So by just by monotonicity we are getting this one, and therefore now what we will do, we will vary over every t belonging to this set. So because for every t this is less, ft is less than equal to fx, therefore its supremum, that is a, will also be less than equal to fx. That's how we prove the first part. And now, as I told, the second part we will do. So what we have supremum, we have to show this is equal to right hand limit. So just by taking the epsilon definition, epsilon delta definition of limit, what we are going to get is, we will take the interval on the left hand side. So what we are going to get is, for this one, we will consider ft between the interval this way, and therefore just by definition what we are going to get, because a is supremum, therefore a minus epsilon for any epsilon greater than 0 will not be supremum. So because it is not a supremum of this particular set, because it is less than the least upper bound, so it's not, for this to be least upper bound called supremum, the smaller than this will not be an upper bound of this particular set. So we have something, some point here in the interval. So let us say if the point has to belong to this interval, that means x minus something. So that's how there exists delta, such that x minus delta belongs to this set, means belongs to this interval. Therefore, f of this will belong to this set, and it is not an upper. This a minus e is not an upper bound. That means this point will be greater than this value. And definitely this, because x minus delta is less than equal to x, therefore it will be less than equal to a, as we have discussed above. So for, because of that we are getting this thing. So we get this condition, and because it's a monotonically increasing function, again we are able to get that if we take x minus delta that side, so f of x minus delta will be less than equal to ft if this condition is satisfied, and then therefore this is less than equal to the supremum of all ft's over the interval. So that's how what we are able to get is that a minus delta is less than this one, and is this is less than this one, and that's how what we get is for all t means what we have a minus delta is less than ft is less than a for all t between this interval. So x minus delta to x is an interval where t varies, and over that we are getting from condition number 4a and 4b. You may pause and try to understand again. That will make it easy to understand, and then try to write it yourself. And that's how what we are getting is that because it is right, it is between the interval a minus epsilon to a, I can easily say that this is less than equal to a plus epsilon also, and therefore ft minus fa is its distance is less than epsilon, where t is belonging to this interval. And that tells me what? That tells me that the right hand limit, because we are taking the neighborhood of sorry, we are taking the neighborhood of x on the left hand side, left hand neighborhood of x we are considering. We are trying to approach to x from left hand side through t. So that is the left hand limit we are getting for function f, that the limit is t, left hand limit is a. So that's how what we get is the supremum is equal to A, which is equal to this one from both the previous condition, as we have earlier in the earlier step we had proved that supremum of left hand side means is this and is less than equal to fx, and that's what we have got, that supremum is equal to left hand limit. So finally that is what is concluded here. That's all. Now, exactly similar way, you can prove this. I advise you all to prove the other part yourself. We are simply writing similarly, but the other part. That means which other part? We are writing this part. We have completed this part, means supremum of all ft, where t is between 0, a and x, is equal to, it is same as the left hand limit of f at x, which is less than equal to fx. That is what we have already proved. Now I advise you, we are simply writing this, a similar part can be done like this. I advise you to do it yourself so that you understand the things better and you are able to do the proof yourself. So this part I am leaving for you to do, and that summarizes the that second one. And where it is written the second statement, if you see the further part, what is written in the further part, we are saying that uh, x and y, if x and y are between a and b, then if we find out the right hand limit of f at x and left hand limit of f at y, they should obey this, they should follow this inequality. For x, the right hand limit should be less than equal to left hand limit at y. So let us do this one. So what we get in this one, so we are considering the assumption that we are taking x and y between a and b with x less than y, and we have to now show that f of x positive is less than equal to f of y negative. So what is the definition of f of x positive? It is infimum of, that is we have done just now, means we have, it's not definition but we have just proved. So it's that we have proved that this is same as infimum of ft, where t is between x and b. That means right hand side of that x. So we are able to write it. And if you see, means because it will be infimum is being attained near x only. So even if I change the sub interval, so instead of going up to b, if I go only up to y, it is not going to change, because this interval x to b is sub interval of x to y. Sorry, x to y is sub interval of x to b, and the infimum is being attained at x only. So what we are going to get is this interval is not going to affect if I shrink the interval from x to b to x to y. So that's how the infimum is going to remain same. That's just a simple trick. We are going to use it for comparing, And now let us see, because two things we have to consider. Fx positive, that is what we have written this way. So it is between in the interval x and y. That's the purpose, so that we are able to compare x and y there. We are writing like this. Now let us do the similar thing with f of y negative, that means left hand limit. So left hand limit, as we have already proved, or we have written similarly, means that way. So f of y negative is what? Supremum of the left side, means left interval. So left supremum of t over t belonging to the left interval a to y. We are stopping at y. And now again, because this supremum is will be for this monotonically increasing function, the supremum is going to be attained at y, as the infimum for a monotonically increasing function was attained at x. So means it is because we are coming on the right hand side, so infimum will be attained like here on x. If we are increasing on the left hand side, in the infimum, the supremum will be increased, supremum will be attained at the right hand side, that means y. So we don't need to change y, but we can shrink definitely from a to y to x to y. The reason is the x is this interval, means x to y is part of a to b. That's how we are able to get. So we get these two conditions. Now just we have to compare that we are considering infimum of ft, where t belongs to open interval xy. And here also the interval is same, t belongs to open interval xy. So we are considering infimum of ft and supremum of ft. As we know that infimum of a set is less than equal to supremum of a set. So therefore, because this one is equal to this and this one is equal to this, so using the inequalities of right hand side, we know infimum is less than equal to supremum. We get that f right hand limit at x is less than equal to f left hand limit at y, and that proves our theorem. So that's what is written, and it's concluding this result.